Hi. Yesterday was the first day I did lead code after a very long time, and then that was very dumb question. But today I opened and wanted to see if the quality of questions have improved or what's going on in this whole lead code scene. So I opened this, and this is the today's daily problem, and I found it very interesting because this is a kind of problem uh, which I wanted to record for our channel because this involves both recursion and based on the constraints. Do you actually need to do dynamic programming or not? And then this also involves some kind of a bitwise OR operation, and cracking that bitwise OR is also interesting. So I wanted to record my intuition and then solve in front of you guys because when I haven't solved this. So first let's see what the problem says. So we have in this example you see we have two numbers 3 and 1. So what they're saying is we need to find the bitwise OR of the subsets. That is, it can be 2 2 or 2 2 2, anything. Like here, since we have two numbers, it can be 3 1 or 3 1. So bitwise OR is of 3 comma 1 is 3. So and then we need to find out how many combinations will give us the maximum bitwise OR. Here you can take, for example, the maximum bitwise OR which you can form here is 3. I will go into detail how I am calculating it. And then there are like two ways you can do it. You can either have only 3, so the bitwise OR of that number itself is just the number, and then bitwise OR of 3 and 1 is 3. So you have two numbers which have the maximum bitwise OR, and that's the answer. So that's what we need to do for this problem. Let's first let me take a couple of examples. I think you'll be clear with the problem statement. Technically, we need to find some kind of an maximum R of the numbers. It can be 3 comma 5 can be the maximum R. 2 comma 1 can be the maximum R of the whole sequence. 3 2 1 5 can be the maximum R, whatever. So we need to find that number and see what are the combinations which we can form out of it. First, we need to understand about subset. Suppose you have number 1 2 3. The different kinds of subsets you can form is one empty set. It can be 1 1 comma 2 1 3 2 3 1 2 3. There is 1, there can be 2, there can be 3. So this is 1 2 3 4 5 6 7 8. So if we have three numbers, we are able to form 2 power 3, that is 8 subsets. So if you don't want an empty subset, then it is 2 power n minus 1. If you want proper subsets, because 1 2 3 is just the set itself, even though mathematically it says when it's a part of the subset, if you want to exclude that also, it will be 2 power n minus 2. This fact is needed here to understand whether we need to do recursion or dynamic programming, which I will explain in a bit. So first, we need to so we'll think in a brute force approach. So we have 3 2 1 comma 5. First we need to find the first part of this problem is finding that maximum R. How do you generally do it? I can pick random numbers here, 1 3 or 2 5 and so on. So the first brute force idea is I will do some kind of a recursion to pick values here. One way is either I can pick 3 or skip 3, pick 2 or skip 2, pick 1 or skip 1, pick 5 or skip 5, and form the solution. In this case, in 1 2 3, you get a solution, you get a subset 1 because you've been skipping 2 and 3. You are able to get 1 and 2 because you just took 1 and 2 and skipped 3. 1 3 because you had chosen 1 and 3 and you skipped 2. So every number has like two possibilities. Either you can take that number or skip that number. So this is a spectrum of problems which comes under 0/1 knapsack. So 0 1 knapsack, what it says is either you pick that value which is 1 or you don't pick that value 0. and you eventually form all kind of a combination. I will write some kind of a pseudocode here. Suppose we have 3 and 1 here. You can either pick 3. Suppose if I pick 3, I will have 3 in my answer. And then I'll first do, I'll just have temp or answer is equal to 0. And then when I first encounter 3, I'll do an OR with 3. So that will be 3. And then what I can do is I can either pick 1 or skip 1. If I pick 1, I need to do this answer is equal to 3 and OR of 1. And I will get some answer. That will be one possibility. And another possibility is with just 3 and skipping the 1, I have answer as 3. I need to always pick the maximum value. If I draw a tree out of it, 3, 1. So first you can either pick 3 or skip 3. If I pick 3, I will have 3 in my bucket. If I skip 3, I haven't chosen any number. So answer is still 0. And still I have two choices, either to pick 1 or skip 1. If I pick 1, I will do OR of 3 and 1. If I skip 1, I will just have 3. Similarly here, I have two options, either to pick the 1 or skip the 1. If I skip the 1, already I don't have anything, so I will still have 0 and I will return because I have reached the end of the array. If I choose 1, then OR of the 0 and 1 and I will return the answer. So this will calculate one answer. This has returned 3. This will calculate an answer. This will calculate an answer. And then with this answer, I would again need to do, this is a smaller problem. So here I need to again do OR. And here I need to again do OR. And then finally with that result I need to do OR. And then I will get the maximum value. So this is the most brute force approach to just find the value. After finding the value, we need to repeat all of these things to identify the number of combinations which we get, tallying it which equals this max. So we are literally doing recursion twice here. Just if you look at it, first we do a recursion to find the maximum R, and then we do another recursion to see what are the combinations adding up together which gives us this max. But do we need to actually do the first recursion? This is where this problem becomes interesting, because we need to find the maximum possible bitwise R, 3, 1, the first example. First of all, let's see how do we actually do a bitwise R. Take example 1 here. The binary representation of 1 is 0, 0, 1. For 3, I'll do this L division divided by 2. I have remainder 1, divisor 1, quotient 1, and then remainder 1. I can't divide it anymore by 2. So I get 1, 1, which is 0, 1, 1. For 1 it is 0, 0, 1. For 3 it is 0, 1, 1. Now I need to do R of both the numbers. R of A and B is, seeing what is maximum here, R of 1 and 1 is 1. R of 0 and 1 is 1, because it is literally true or true. False or true is always true. False or false, it is always false. So I get 0, 1, 1, which is nothing but 3 here. So what can we observe from this? We have 0, 0, 1, 0, 1, 1, 1 and 3. Look at a pattern here. We need a bigger number here. Some possible way I need to make, suppose I have like 100 numbers here. Even if one number has 1 here, that is more than enough for me to say this whole bit will be 1. Similarly here, even if one number has 1, any one bit has 1 here, and eventually you do OR of everything, that will be 1. Similarly here as well, since here there is no bit as 1, we have no other choice to write it as 0. If we see a 1 here, so any if we have like 99 numbers in front, doesn't matter. One number has 1 at this place, so r of everything will eventually be 1. So with this we can understand one thing: the larger our sample sizes, here we have 3 1. Suppose we have another number, there can be a possibility that there can be 1 here. So how do we approach it greedily? Greedily, what we say is, suppose we have n numbers. If I r every number, there is a possibility that some number can or cannot have the byte set. You have 3 2 1 5. Assume byte is set as 0 for both 3 and 2. But there can be a possibility that since we have a 5 here, there can be a possibility that byte can be set to 1, so which eventually adds up to 1. So greedily, what we can identify from this is, if we have n numbers, if we try to do r of n numbers, that will be the maximum r possible by any numbers in the array. You take any other smaller subsequence which can equal to the r of all numbers, but we are pretty much sure that the more we try, we have a higher possibility that a byte can be set to true, and setting a byte to true is will give us maximum result. How? Let's take 0 1 1 and 1 0 0. If we know bit manipulation, just converting, we are trying to first convert this binary number into decimal. How do you do it? This is 0th bit, so 2 power 0 into 1, 2 power 1 into 1, 2 square into 0. Suppose we have this 101, this is 2 power 0 into 1, 2 power 1 into 1, 2 square into 1. So if we add this up, it is 0 plus 2 power 1 plus 1 2, 2 power 0 is 1 plus 1, so which is 3, and if we add it, it is 2 square plus 2 power 1 into 0 plus 2 power 0 into 1. We're setting this bit, so 1, which is nothing but 2 square, which is 4 plus 0 plus 1, which is nothing but 5. So the more bits we set, it becomes 1. So we multiply it by 1 so that we get a huge number. Since this bit is not set, we multiply it by 0. So this will be 0, of no use. If it is set to true, or if it is 1, then we will definitely multiply it by 1. So we will definitely get a number. So we need to create more chances such a way that we get a 1 here. How do we create more chances? By trying out more numbers. If we have 3 numbers which doesn't set this byte, there can be the 4th number which is in the array which can set the byte true. So we don't have to lose that opportunity of trying out. So when we try out n numbers, there is we are pretty much confident that since the more number we try, there is a more higher possibility of getting a maximum number. So greedily we can identify that if we have n numbers, we just need to r all the n numbers to get the maximum r of n numbers. With this, we just reduce one recursion call here. So we've cracked the first half of the problem, that is 3 comma 1. Now for 3 comma 1, the max is just r of all the numbers, which is nothing but 3 here. Now we need to look at the second half of the problem, which is nothing but classic 0 1 knapsack, but with a little twist of not just adding numbers, but here we need to r numbers. So what the second half says is, we need to find all possible combinations, all possible subsets, such that rring all the numbers in the subset should give us this max value. So here 3, first I can either pick 3 or not pick 3. If I pick 3, initially the value is 0, so 0 or 3 is 3. So I have another possibility of picking 1, not picking 1. If I pick 1, if I pick one, the now since the R value is 3, 3R1 is 3, and there is no other possibility here. So we got a result of 3, which is what our required result. So I'll return 1. That is, there is one subset 3 comma 1. There is one subset 3 comma 1 which gives us this maximum R value. And here, if I'm not picking up 1, I will still have R as 3, which is which is what we need. So here also I will return 1. And then in this half of the tree, since I haven't chosen 1, now I have a possibility to choose 1 or not choose 1. If I choose 1, I get value as just 1, because until now it is 0. So it becomes 0 or 0 is 1, which is not what we want. So this will return 0. And if I am not picking, it will again be 0, which is not we want. I will return 0. And then I will just add this up. So adding 1 and 1 will give me 2. Adding 0 and 0, which will give me 0. And we go another up, level up. And then now 2 plus 0, which will give us 2. The final result is 2. This is the base recursion. You can think of now the next step which you will take is to think, okay, now should I solve this problem using dynamic programming, or is there a possibility to memorize this code or tabulate this code and optimize the code, or is it enough for this solution? That's when I'm gonna talk about something very crucial here. Looking at the constraints. The constraints clearly say that the number of elements in our main array can be at max 16. What does this say to us? So if there are n elements, there are 2 power n subsets, which we have already declared. So there can be at max 16 elements. So we can have at max 2 power 16 combinations. So we need to, so in the worst case scenario, if we have an array of length 16, our program needs to work on 2 power 16 combinations. If writing an recursion solution, will it cause time limit exceed? Assume in C++, 1 second is approximately 10 power 8. So, which is nothing but 10 power. So most of the compilers here, the competitive programming compilers, have a limit of 1-2 seconds max. So take this example. Let's be on the safer side and let's consider this as 1 second. So we need to make sure our code runs within a second, which is nothing but it can handle 10 power 8 combinations. So 10 power 8 is nothing but 2 power 8 into 5 power 8 and 2 power 8. Let's keep it as 2 power 8. And so the right way to always apply logarithm on both sides and calculate 5 power 8 using your log table, which you did in your school, and then multiply it with, and you will get a value. So, but I just don't want anything exact. I just want to see if our 2 power 16 is well within our limits. That's it. So we have 2 power 8 into 5 power 8, which I am 2 power 8 into 2 square 8 into something else. And then this is nothing but 2 power 16 into something else into 2 power 8. So 2 power 16 plus 8 into some number, because this 5 power 8 is not 2 square to the power 8, right? Which is some kind of an approximation. So which comes up 2 power 24 into something, and 2 power 16 is way lesser than 2 power 24. So our normal recursion solution is good enough for us to compile. So this is one aspect of it which we need to consider, because we all do competitive programming in a very time-bound environment, and we don't want to waste time in optimizing. And because optimizing this, if you can write this recursion solution, and optimizing this takes a couple of minutes, but every couple of minutes you lose thousands of rank, right? So you can just pretty quickly figure out, okay, 2 power 16 which can be inside our 1 second limit. So that's the reason why I am not going to do dynamic programming optimization here. I just wanted to write the recursion solution, and I think that that will be enough to pass all test cases, and I won't get time limit exited. Let's see how I'm going to implement this whole recursion and recursion. I haven't seen coded this before. As you've seen, I'm just going to code with you guys. So first step is to, since I've explained everything what goes on, I have a pretty good idea on what all I need to do. First one is to get the maximum R and then find possible R combinations which tally up to the maximum R. So why I am taking as 0? Because binarily 0 is 0 0 0. So when you do R with that number, it doesn't matter. So maximum R is nothing but maximum R with the number. So now I will have the maximum R. So with this we need to now find our required result. 0 is the starting index of the number, because we need to go from 0 to n minus 1, because we need the base case for our recursion, and then the nums array itself, and then I will send max R, and we need some kind of an intermediate result as well, because this intermediate result eventually we need to compare this result with the max R, whether they both are equal or not.
So solve it is in I vector and nums in temp then in max.
The first thing you always write in recursion is the base case. What is the base case here? When do we need to exit the recursion? If you see this diagram, we exit the recursion the moment we reach the end of this array, because we have exhaustively searched through all the results and there is nothing more to search here, so we return back with whatever result we have. So that's the same thing. If I is greater than or equal to nums dot size of, I would return if temp equal to max R. At this point I will have some temporary result. Here you see the temporary result is 3, which I will compare with the max R, which is 3. If both are equal, I would return a 1, because we found a pair which satisfies our condition. If it isn't matching, I would return 0 here, because we haven't found a pair. If it is equal, I'll return 1, else return 0. This is a ternary operator in C++. You can always write with if case. And then now the base case is done. Now comes the main case. We have two possible options, either to pick the answer or not pick the answer, which is the core idea of 0 1 knapsack. If I pick a value, what happens is I will move on to the next number. Suppose if I pick 3, I will move on to the next number 1. So I am incrementing the index. The nums array is still the same. And then what happens with the temporary value is, temporary value I will R with this nums of I, because as of now the temporary value is 0. When I find C, I'm thinking of, okay, let me pick this value. So what I will do, I will do R with my temp, which is 0. So 0 or 3. So that's what I'm doing here. And then as usual, this max R doesn't matter, which will always be constant. And if I'm not picking anything, suppose if I'm skipping 3, what I will do is I'll just move forward. The nums will always be same, but here, since I'm not doing anything, I'm just ignoring it and moving forward, the temp still remains temp, and then max R remains max R. If you look at this graph, I have ignored the value, I have picked the value, and finally it hits the base case and it returns some answer, either 1 or either 0. So what I'm doing is I'm just Fetching the value it gives 1 and this gives 1, and I am just adding both the value and pushing it to the level above. So I'm doing the same. So I will just return. So this pick, after picking and everything, it'll give me some answer, and not pick it'll after doing all of its thing, it'll give some answer, and all I need to do is I need to just add them up and push it to the level above, and then finally I can return answer. Let's see if this works. Let's debug. Oh, okay. Looks like it satisfies all the cases. Let's see if it passes within the time limit. Yeah, it did pass. I hope you like this video. I think you learned something out of this video. So I'm thinking of being a little bit more consistent with LeetCode, but if there are problems which are very interesting like this, I would like to cover as a YouTube video. Yeah, so I think you learned something out of this. Let's catch up with some other interesting video. Thank you.